welcome to the other part of the course. Today I'm going to talk about the history of cochlear implants. So, the overview of my lecture will include the challenges of the CAI innovation. So, I will talk about why the cochlear implant innovation has been so hard and so successful. The other thing I'm talking about is a historical development from timeline of innovation and about the time when and how cochlear implant come to the world. I'm also talking about the Lasker Award. It is recognition of cochlear implant innovation rich in history. Lasker Award was one of regarded as Nobel in the medical field. So I'm briefly mentioning about that. At the end, I will talk about the future development and future function of cochlear implant. What I think is the challenges ahead, what can be done in the future through cochlear implant. So first, the challenges. So why it has been so difficult to develop the cochlear implants? First thing is, we are trying to replace the sense of hearing with the electronic device. And we know the cochlea itself is a very complex organ, including outer ear, middle ear, inner ear. And each sections has complex mechanical physiology mechanism behind. And using a simple medical device, electronic device, how we can replace a sense of hearing. And actually, as a matter of today, the cochlear implant is the most successful devices that have replaced one of sense of hearing, one of sense of our human body. The other challenge is back into the time. At the beginning of the development of the cochlear implant, really the inner ear is a forbidden zone. Seen by ENT doctors, agreed by lots of people, surgeons, they don't want to touch it. They don't want to touch anything about inner ear, which these things can be dangerous, leading to infections. And most importantly, at the time of invention of the cochlear implant, at the stage, many scientists, they don't believe the principle, theory behind a cochlear implant. They just say, well, they simply would not be able to deliver a level of speech understanding or a level of hearing sensation equivalent to a human body. So here, example of the cochlear organ. What we're trying to do, a cochlear implant is trying to do, is really replacing the outer hair cells. So when you insert a cochlear implant, it replaces the sensation from the inner hair cells and outer hair cells. It directly stimulates auditory neurons. But think about how many auditory neurons in our body, and how many outer cells in our body. There are at least 3,500 outer cells in the ear, and also thousands of neurons in the organ cortex. So that is really the challenging. If you think about the electrodes you only have 6, 12, or 20 electrodes. And you need to use these electrodes, almost replace all these sensory neurons, which is really difficult, challenging task, which is also part of the reason why many scientists don't believe it's going to work. So coming back to the innovation, at the beginning of this electro hearing, the idea is using electronic signals or electric signals energy to produce a sensation of hearing is actually first reported by Italian scientist called Waltz. So he developed the battery, and then he did an experiment, try to see how much you can hear of hearing the electricity. And also talking about the hardware development, multiple channels of cochlear implant hardware development. And also I'm going to talk about the speech coding strategy development over the last few years. So Waltz, he's supposed to be the first person did recorded the sensation of electric hearing. So he write it down in a scientific journal or some diary. He said, I received a shock in the head, and some moment after, I began to hear sounds. It was kind of crackling with shocks, which I believe it might be dangerous because of shocks in the brain. That was a very interesting diary recording of how the electric currents could be heard in the sound, and that actually is the first evidence of a human being trying to hear transition from electrical energy to be the sensation of hearing. But probably what he wrote is quite dangerous, that prevented lots of people trying to do the similar experiments. It's only after about another 150 years, then people start redo the scientific psychophysical experiments. But obviously in 1930s, 1950s, at that time, people have much more power to do the scientific experiments more thoroughly. So Stevens in 1937, they did some electrophonic perception, they called. They did exactly trying to sending the electric currents and trying to understand what is the driven mechanism behind why people perceive sound. Actually, they separated out into different elements of the reason why we can hear this electric sound. Actually, there's some part of mechanical because of tympanic membrane, also some vibration, also some sensation of the outer cells movement. So that is very interesting, looking back, an early stage of how people trying to convert the electric energy to a sense of hearing. And the first experiment really recorded is by this French scientist. He tried to do is really on the deaf patients. These two deaf patients are profound deaf and totally deaf patients. And he did put electrodes into the in the ear and trying to measure to see what is profound deaf patients can have a sense of hearing. And that was done in 1957. And that was the first recorded experiment done to people with hearing loss. And following that, actually, the animal models electric hearing in the 1970s have been is done, and then they trying to understand more electrophysiology models and why and how these non-electric signals, electric current, can become a sense of hearing built on the new animal models. So in 1963, actually, the modern cochlear implants becoming formed from really prototype experiments, animal study, become become a clinical device. So the House 3M single electrode implant, that was in 1963, that was the first device, was American FDA approved a clinical device used in patients, but the limitation is only single electrode implant. But amazingly, it didn't provide much benefit for speech understanding, but still it caused it is first clinical device that is used on patients that can give them a sense of hearing and some kind of words understanding. In the 1970s, they developed these implants. Before, these implants always has a plug, so it's not a percutaneous. But now with they developed the cochlear implant, it become much more variable and smaller, and also with a magnet on the head and the internal part, outer part. So you have an internal part electrode completely under the skin, and the external part is just with a magnetic and connection with the internal part through the magnetic field. And in 1977, and so that's now is a model in Vietnam, in Austria. The Hochmer, they developed the first 8-channel electrodes cochlear implants. So that's here. And also in 1978, in the other part of the world, in Australia, in Melbourne, so Graham Clark, so he formed later, become a company called Cochlear, and they also developed multiple channel cochlear implants. So at the time of 1970s, 1960s, a really exciting time and lots of innovation happening around the world. So including France in 1957, close to 1960, and also in Paris, in Vietnam, in Australia, and coming back to America in Los Angeles. These all become very powerful companies later on. But that's a really exciting time for cochlear implant innovation. During that time, cochlear implants becoming more usable, becoming much more efficient with the time of development, and also the channel numbers generally has been increasing, and also shows the improvement of people's understanding. So what I just described is a very brief history of cochlear implant development, really from the early stage of just to see whether they can hear a sound from electric stimulation to the journey become a clinical device. But here, this is another important part is the speech processing strategy, as I mentioned in my some of lectures before. So the speech coding strategy really is how you can transform acoustic energy into electrical pulses. So the strategy basically is how. It's like a recipe of the cooking. You define how the signal is transformed, which part of signal you want to select to stimulate the neurons. So along the timeline you can see here from 1980s to 2002, that's see an increasing coming with different speech coding strategy from different companies. And the y-axis is really the speech recognition score. You can see from 1980s in the early stage, the single electrode, it provides limited, very limited benefit. It's below 10% of speech recognition score. But as you grow into 1980s, 1989, until coming to 2000, the speech understanding has reached more than 80%. But interestingly, the speech coding strategy used is really from very, very simple ones like F0, F2. They just based on the formant, based on the energy of the speech signal, to more complex type of algorithms. For example, these peak-based and selection channels only select the channels which have high energy to stimulate the implants. And also the ACE is really a breaking point to see how the performance has improving. But after 2002, actually the performance, there's still some improvement over the time until now. So last probably 17, almost 20 years. But actually the performance almost plateaued, so they reaching 80-90%. If the children implanted in early stages, the children expected they can easily getting 90% of recognition inquired, depending on the material you use, depending on the situation in the lab environment you're testing. But in general, it's very good. But the challenge really is in noisy situations. In noisy situations, we're still looking at around 60, 50, or for some patients even worse. In the noisy environment. And so that is a challenging ahead that I'm going to explain later for the future challenge of cochlear implants. And I also want to use this opportunity really to mention the Lasker Award in 2013. So Lasker Award is a Lasker Foundation. The award, the most prestigious, they think the most beneficial intervention in the medical field to people. And so in 2013, cochlear implants was picked up by the foundation, by the committee, and they regard it as a Nobel Prize in medical field. So three people got a prize. So there is in University of Melbourne, so that's Professor Clark, and also in Madel in Austria. So in the middle is Hochmer, and then the last one is Duke University, Blake Wilson. So these three people, they were really the founder of this cochlear implants development. And later on, they all developed becoming commercial company as well. Like Clark is founder for the cochlear, Madel is involving as founder for the, Homer is founder of Madel, and then Blake Wilson is involving the Advanced Bionics. So all these three companies are now the biggest three companies, cochlear implant companies in the world. So for Clark, for Professor Clark, really is his father has a hearing loss and he's an ENT doctor. It's really interesting to see how the inspiration and just from simple concept he want to help his father to hear better. Then he determined to make this device. Goes through lots of challenges. And Homer is from Vietnam, and actually this was the only biomedical engineering student or biomedical engineering scientist in Vietnam at that time, and she joined her boyfriend at the time, later become her husband, to develop this cochlear implant product. And Blake Wilson, the main contribution really is about the CIS strategy. So it's called continuous interleave sampling strategy. And this strategy really make the jump, help the cochlear implant's performance from really low percentage, 40-50% jump to like 80, 70, 80%. And that's really a big achievement. So these are three important people contributed to the cochlear implant development. Of course, they always have a strong team around them, and lots of scientists have been working behind the scene and developing algorithms, developing the design, and also developing the electrode development and also surgery technique. So it's really a great team effort, and really very inspiring to see cochlear implants coming to helping potentially millions of people with great team effort together. So what's the future for cochlear implants? What are potential interesting points I think the future cochlear implant could bring? I think first one is really the connectivity. The connectivity has been happening in hearing aid world. For example, you can make a phone call, you can stream in music through the hearing aids now. It's already a few companies bring out. But so far, cochlear implants still need to rely on intermediate device. That is, in order to hear the phone or from a Bluetooth, or you want to stream in music, you need an intermediate device to be able for patients to hear them. I think the next step really, it's probably in the next few years really happening, is when you make a phone call or anything exactly like hearing aids, the phone call should be directly streaming the signals into the cochlear implants, and the patients just pick up the phone call and they can hear straight away. And the other bit is noise reduction strategy. As I mentioned previously, the noise issue is really the most critical or challenging thing in the world for the cochlear implants study, because lots of people they are very, very good in quiet situation with cochlear implant device. But once you put them into noisy environment, then the performance really just going down quite significantly. And this is actually involving in the principle behind the design of cochlear implant behind. Really, in the early stages, the design didn't think about it quiet or noisy. They're just thinking, well, how we can pick up information and to stimulate the neurons understand the pulses, then sending the signal to the brain, then the brain interpret these signals to be speech. But I think about it in the noisy environment, the information you send in should be quite different from what you send in a quiet situation, and that hasn't been considered in a more systematic way. So the noise reduction, hopefully, in the next 10-20 years, will be involving, for example, artificial intelligence, or involving some super good noise reduction algorithm. It reduces noise, same time keep the intelligibility of the speech signal. And the third thing, the fitting. So the fitting at the moment, the cochlear implant fitting relies on mainly trying to find out. You will find out also in other lectures about the cochlear implant fitting. It's really trying to find out two or a few parameters. Really, one is about the threshold level, so the quietest sound you can hear. And the other is the highest level the cochlear implant electrode will stimulate across all the channels. So each electrode need to find two levels at least. One is the minimum level, which you can hear, and the other level is the highest level you feel comfortable and not feel discomfort. That high level the cochlear implant stimulation will be, which done across all the electrodes for each patient, become an individualized fitting. But we found that fitting process really is time costly, and also sometimes think about reporting back how loud it is. It's really difficult for people who haven't get access to hearing for a long time. It's like if you're blind, then later on you got a device asks you judge how bright the color is, which color it is, or how bright it is. It'd be really tricky to judge that. So lots of companies has been investigating how we can use some objective measurement. For example, ABR methods, auditory brainstem responses, or the stipity reflex. So all these objective measurement, patients don't need to tell you how loud they think how loud it is, but this measurement will automatically tell you approximately which is the level the patient will feel discomfort. So the automatic fitting will be a significant part. And also plus the whole population, the training audiologists and training specialists to be able to fit in the cochlear implants, we don't have that many audiologists can do it. Actually, we don't have many audiologists, particularly in some world developing countries. So it's really important to develop some automatic fitting protocols. And the other part I really like to mention is the hearing preservation. The hearing preservation is a huge big topic in the cochlear implant world. So before you just want to put this in and get as a higher performance as you want. But now the hearing preservation is really on the table now. You have to measure before cochlear implants, and after cochlear implant you measure again to see how much hearing has been damaged, how much hearing has been preserved. So lots of technology from different companies are trying to introduce, particularly in the surgery technique, how you can insert the electrode as much as possible or as good as possible, and at the same time you try to preserve a residual hearing. And the other function of cochlear implants is drug delivery. And it has been trialed in a few centers and has been also used in some clinics. They try to use in cochlear implants now. The cochlear implants is already inside the inner ear and inside the head, basically. So you use that as an intermediate device to send in drugs and locally into the inner ear. The other development of a cochlear implant is really make a cochlear implant become a completely implantable device. So it's completely, when you have a cochlear implant, you can't see it. There's no external body part. The external part and internal part is just merged together. Charging will be through wireless, and that already in the investigation, and I think it'll come up in if not 5 years time. So thank you very much for the listening. I hope you enjoy the rest of the lecture.